Hello everyone. In this video we're going to explore an interesting relationship between two concepts that we're already familiar with, namely radicals and powers. And until now we may not have realized it, but there turns out to be an interesting connection between the two. So for starters, let's consider the square root of 9 and see what happens if we were to square it. Now we know that square root of 9 is just 3, so when I square it I end up with 9. Now in fact this is true if I take a general expression like the square root of x and square it. As long as the expression square root of x is well defined, meaning as long as x is greater than or equal to 0, we know that this is going to result in a very similar situation. And just like square root of 9 squared turned out to be 9, the square root of x squared will turn out to be x. This is going to be one of the key relationships that we're going to be using throughout the rest of the term. So we want to become very comfortable with that notion. Now, I also notice if I were to take 9 to the 1/2 and I square it. Now, until now, we've never encountered anything like this, where an exponent is anything other than an integer. We've dealt with positive integer exponents, also known as natural numbers. We've dealt with negative integer exponents, and we've dealt with those with the formula x to the negative n equals 1 over x to the n. And also zero exponents. We know that x to the power of 0 is 1, but we've never had a fractional exponent. But for a minute, let's assume that we can apply the laws of exponents here. So if you recall, we have a power rule which says if you take a power and find a power of that power, then what you need to do is keep the base and multiply the exponents. So if I apply this rule which we just mentioned, here we end up with 9 to the power of 1/2 times 2. And I realize that's 9 to the power of 1, which of course is 9. So there seems to be an interesting relationship here. So this brings us to the notion that maybe square root of 9 and 9 to the 1/2 are the same thing. And in fact, they are whenever the square root is well defined. So we generalize this notion for all nth roots in the following manner. We say the nth root of b is equal to b to the power of 1 over n whenever the nth root of b belongs to the set of real numbers, meaning basically it's well defined and it's a real number. So this actually gives us the ability to, for the first time, handle fractional powers such as b to the 1 over n. For example, if we were to look at 16 to the power of 1/2, if we apply this rule and convert this 16 to the 1/2 to its radical equivalent, we get, notice that the denominator here is going to become the index in the radical expression. So it becomes the square root of 16 to the power of 1, which is, of course, the square root of 16 if you recall, when it comes to radicals, because square roots are so common, we usually just leave it blank. So when we leave it blank, it doesn't mean there is no index. It just means the index is assumed to be 2. So now we know what the square root of 16 is. Remember, that's the positive or principal square root of 16. So that's 4. So we can do these kinds of computations with fractional powers by first converting them to the more familiar radical form. So we can do the same thing, for example, with 125 to the power of 1/3, which, as we apply this formula, becomes the cube root of 125. And if you recall from the tables that we were asked to memorize in our last lecture, this is 5. When you see the cube root of 25, the question you want to ask yourself is very simple. What number do I cube to get 125? And of course, that number is 5. So now, when it comes to negatives, you have to be slightly more careful. So for example, suppose that we want to calculate negative 81 to the power of 1/2. Now, notice here, the negative is not being raised to the power of 1/2. Here, the only number being raised to the power of 1/2 is the 81. So we can go ahead and say this is equal to, here we're just going to carry the negative, and we're going to write it as, using this formula conversion, we're going to write it as the square root of 81. Now that's a perfectly well-defined real number, and we know that it's -9. So if we were to look at -81 to the power of 1/2, however, we'll end up with the square root of -81. And as we well know, there is no real number whose square is -81. So we want to be very careful not to say it's undefined, because it is a well-defined number in a larger set, which we will explore later, called the set of complex numbers, as already mentioned. So what we will do is we'll just simply say it's not a real number. That's all we can say for now. So make sure, know the difference, right? Know the difference between -81 to the power of 1/2 versus -81 in parentheses to the power of 1/2. So make sure that you absorb this before you continue. Of course, as you have probably guessed, we'll have this situation with negative numbers and indices that are even. So for example, if we have, say, -81 to the power of 1/4 as opposed to -81 quantified to the power of 1/4. So in this case, as you know, the negative is just going to carry. So we're going to get -4th root of 81, which is a well-defined real number known as -3. In this case, we're going to get the 4th root of -81. And as we know, there is no real number that we can raise to the power of 4 to get -81. So once again, here we will say not a real number. This notion carries on to fractions as well. For example, if we have -49 over 25 to the power of 1/2, as opposed to negative 49 over 25 quantified to the power of 1/2. So on this side, we know that we will get negative square root of 49 over 25, which, as we well know, is negative 7 over 5. But on this side, we'll get the square root of negative 49 over 25, which once again is not a real number. Now, we don't run into a similar kind of issue with odd values of n. So let's remember the formula, the nth root of b equals b to the power of 1 over n. So, for example, if we have the expression, say, negative 32 to the power of 1/5, we know that that ends up being the 5th root of negative 32. And if we look at the prime factorization of 32, we know that 2 goes into it 16 times, 2 goes into it again 8 times, 2 again. And remember, when you do a prime factorization in this manner, on this side, you only want to put prime numbers. So 2 goes into it again 4 times, 2 again twice, and 2 1. This process of prime factorization comes to an end once you reach the 1, because we know that we are finished at that point. So we know that 32 is 2 to the power of 5, but since we have the negative, we know that this is going to end up being negative 2. So there is no problem with taking an odd root of a negative number. That doesn't result in a situation where we have to say not a real number. And interestingly enough, notice that if the negative were outside the parentheses, it would make no difference. Because in this case, the negative would carry, and we would just get the 5th root of 32, which, as we know, again, is negative 2. So not the same kind of situation when it comes to negative numbers and odd values of n, as either the index here or the denominator here. So those are subtle differences that you really have to start becoming aware of if you want to move into more advanced mathematics. Now we'd like to see if we can extend this to the situations where the numerator of the fractional power is no longer 1. Remember, we already know that b to the power of 1 over n is equal to the nth root of b. Now, as long as, of course, the nth root of b is well defined. So what if, instead of 1 over n, what if I had b to the power of m over n? Is there anything that we can do to convert that to a radical expression? And of course, we realize that if we do a little bit of an algebraic trick here, we can, of course, write this as b to the 1 over n to the power of m. Notice that here we used the familiar rule x to the m to the n equals x to the mn, the power rule from exponents. And notice here that 1 over n times m, we can always throw 1 under the m, and that just becomes m over n. So this rule will in fact end up giving us the same expression. And now we already know that b to the 1 over n is the nth root of b from right here, this rule that we've already been exploring earlier today. So this becomes the nth root of b to the power of m. Now, if we take the same expression b to the m over n. Notice we could have applied this rule just slightly differently. We could have put the m on the inside, and we could have put n on the outside, the 1 over n on the outside. So this would have become, we can also write this as b to the m to the power of 1 over n. Notice we're just changing the place of these two, but when we multiply, we're still going to get the same m over n. So I can also realize that the nth root of whatever is going to be that whatever to the power of 1 over n. So here I can say this is the nth root of b to the m, which brings me to the ability to write now this extended identity, which b to the m over n equals, first I'll bring this over, which is equal to the nth root of b to the m, which is also equal to this expression. Remember, both of these are equal to b to the m over n, and of course that means they're equal to each other as well. So this is called the transitive property. We say that if a equals b and b equals c, that implies that a is also equal to c. So we're going to apply this transitive property, realizing the fact that since b to the m over n is equal to this quantity and also to this expression, then these two expressions must be the same as well. So we have the nth root of b to the m, and this equation right here, or this identity, is going to be one that we're going to use quite heavily because it implies a great deal of efficiency. So if we want to find the nth root of a power, what it tells us is we can take the nth root of the base and then raise that to that power, which is a really efficient thing, as you will see in an example in a second. Suppose, for example, we want to find the cube root of 27 to the power of 4. Now, 27 to the power of 4, as you know, is 27 times 27 times 27 times 27, right? It's not the quickest, simplest multiplication, and it's a very large number. But however, who would want to calculate that if they didn't have to, correct? So, and as it turns out, because of this nice property here, we really don't have to, because we can take the cube root of 27 first, and then whatever result we get, raise that to the power of 4. And of course, we end up with 3, because we know the number we need to cube to get 27 is 3. And then we raise that to the power of 4, and we end up with 81. And we achieve that in a much simpler manner than if we had to actually raise 27 to the power of 4. Of course, if we really insisted, we could always calculate 27 to the power of 4, and you can see that you will get a giant number, 531,441. So you could have done this by actually not taking the simple route and just calculating the cube root of 531,441. And then, of course, you would have to sit there and, perhaps do it, if calculators are not allowed, find the prime factorization or something of that nature to try to simplify this. But as you can see, the lifesaver here is this relationship right here, so that we could avoid having to do this. And of course, if you did that, you would still get 81. Of course, now that we're armed with this powerful, more general version of this initial identity that we explored earlier, we can do some more interesting types of problems. So at any point where you feel like you should be able to handle these on your own, please pause the video, do try it on your own, and then come back for maximum benefit from the lecture. So assuming you've tried them on your own, here we get, so we can either put it in this form or put it in that form. We have found out that this form usually results in much simpler expressions for us. So we're going to go ahead and use that form. So notice that the easy way to remember this rule is that you see how over here in the exponential form of this radical form, notice the m is on the top, it's the numerator. So the way we remember it, and we notice that the m is also here as an exponent. So we say high goes high. That's a nice easy way of remembering this identity. So, and we know that the index, which is in a relatively lower position compared to that, is going to become the denominator. So converting from this direction to the right, so from left to right, we get the square root of 36, and then we're going to, once we know what that answer is, we're going to raise it to the power of the m in this situation, which is going to be 3. So we get 6 to the power of 3, which is basically 6 squared times 6, or 36 times 6. And one quick way of doing this in your head, in case you're wondering how some people can do it, you can turn that into 6 times 30 plus 6, which is 180 plus 36, which ends up giving you 216. Or it may be part of your repertoire from the tables that you memorized. Maybe I only showed you how to go to the number 5 as far as cubes were concerned, but maybe you went further and memorized 6 cubed as well, which is 216. Eventually, as you do more of these, you'll remember some of these. All right, so again, do make sure you've tried them on your own before you come look further. So here we're going to end up with the conversion as a radical, where the 5 becomes the index. The radicand is going to be 243, and our outer power here is going to be 2. So now the fifth root of 243, again, that was not one of the ones on our table, but we can always do a quick prime factorization of 243. And we know that 2 doesn't go into it, but we notice that 2 plus 4 is 6, and 6 plus 3 is 9. So we know this number is divisible by 3, because remember, that's the divisibility rule. If the sum of the digits of a number are divisible by 3, so is the number itself. So we go ahead and start with 3. 3 goes into 243 81 times. We know that's divisible by 3 27 times. Again, we have 3, which gives us 9, and 3 again gives us 3, and 3 gives us 1. In case you've never seen this, this is basically what you used to see as a factoring tree. Think of this as the kind of more mature, grown-up way of handling the same factoring tree in a much more compact, efficient manner. So we notice that 243 is indeed, and this is the nice thing about this prime factorization written in this way, everything you see here is going to be all the factors of 243. So we can see it's 3 to the power of 1, 2, 3, 4, 5. So what number do we have to raise to the 5th power to get to 43? Indeed, it's going to be 3. So we know that this is going to be 3, and then we're going to square that to get 9. And there we have our answer in a very nice, simple, efficient manner. Okay, so in the next one, we realize the negative is not being raised to the power of 4/3, so it's not in parentheses, so we're just going to carry the negative, and we end up with the cube root of 64, and once we have found out what that is, we're going to raise that to the power of 4. So here we'll end up with negative 4 to the power of 4, and I do believe we had that in the table that we decided to memorize, and if you recall, that's basically 4 squared times 4 squared, 16 times 16, so 256, like so. So make sure that you fully absorb this stuff. We're going to be utilizing it later and before you proceed while I prepare the board for our next set of problems. So now we're going to take a look at these 3 problems. As always, do try them on your own before you join me again. And that's simple. You just pause the video and try it. So assuming you've tried it, I'm sure you found out that this is going to translate into, let me write down our basic rule here for our assistance. We know that if we have b to the power of m over n, that's going to be the nth root of b to the m, which is also the nth root of b then raised to the power of m, which is the one we usually prefer. So here we're going to get the cube root of negative 64, and then once we have that answer, notice that all of the negative 64 went into the radicand position because it was parenthesized. So the whole thing is being raised to the power of 2/3, the entire negative 64. And then we're going to raise that to the power of 2. So we know that the cube root of negative 64 is the number that we have to cube to get negative 64. So if you think about it, that's just negative 4, and we're going to go ahead and square that, and we're going to get positive 16. Now, these two look kind of similar, don't they? But of course, this one is being raised to the power of 2/3, and this one is being raised to the power of 3/2. And you're going to find out that that makes a really big difference. Because here, once again, we're going to go ahead and get the square root of negative 64 to the power of 3. But notice, there is no real number whose square is negative 64. So this one is not a real number. And of course, if you take some number that is not a real number and cube it, you're going to end up with another number that is not a real number. So here, it's one of those situations we're going to say narn, or not a real number. Okay. So with this last one, it's a slightly different from the ones we've seen, because this is the first one where we encounter a negative exponent on the fraction. So what I mean is a negative along with the fractional exponent. So we're going to have to actually go ahead and use our negative exponent rule, which is x to the negative n equals 1 over x to the n, and make that a positive exponent first. Even when we were dealing with just integers, remember the way we evaluate negative exponents is by actually turning them into positive exponents first. So this becomes 32 to the power of 2/5. So we end up with 1 over, now that's going to be the 5th root of 32, and then we're going to square that result. Now we know the 5th root of 32, in other words, the number that has to be raised to the power of 5 to give 32 is just 2. So we're going to get 1 over 2 squared. So we get 1 over 4. So make sure you absorb this and understand it all before we proceed to the next screen. Okay, so for this next problem here, we can use the x to the negative n equals 1 over x to the n rule for sure. But if you remember from the time that we covered negative exponents, we also had a really nice rule for when actual fractions were involved. Now, I'll just go ahead and go through the derivation that gives us the rule just to jog your memory. Remember, this means x to the negative n over y to the negative n. Now, this rule on the left, if you remember, had a close relative, which is, what if you have 1 over x to the negative n? And that is, what if the negative power was downstairs? Then we know that we can just bring it up to the top and make it positive. So using both of these rules, we end up with having to move x to the negative n downstairs to make it x to the n, and moving y to the n to the top to make it y to the n. So notice we can always write that as y over x to the n, which gives us the really nice rule. So this implies that when you have a fraction raised to a negative power like that, you can always flip the fraction or reciprocate it and then change the negative n to n. So that's the rule that we'll go ahead and apply here. So we're going to take this expression and we want to make the negative 4/3 into a positive 4/3. So we're going to have to flip the fraction, turn it into 125 over 64. And now we can change that to a positive 4/3. Don't forget that this one just changes sign. It doesn't flip or anything like that. All right, so basically we're looking at the cube root of 125 over 64. And once we find that result, we're going to raise it to the power of 4. Now, here we have a question to ask, of course. What number is it that I have to cube to get this number? That's what this means, right? The cube root of 125 over 64. And we know that's going to be 5 over 4. Now we're going to take that and we're going to go ahead and raise it to the power of 4. So of course we get 5 to the 4, which is 25 times 25, so 625, over 4 to the 4, which if you remember is 16 times 16, so 256. Now you should always try to simplify such expressions or such fractions, but here we know that all the factors down here are going to be powers, basically powers of 2, and up here we're going to have just 5 as a factor, so there's not going to be any cross canceling possible. So basically we are done with that problem. All right, so here in the next one, notice that this negative is not being raised to the power of negative 1/4. So it's just going to carry, and we're going to get 1 over 81 to the 1/4. So we get negative 1 over the 4th root of 81. And we know that the number we have to raise to the power of 4 to get 81 is 3. So we get negative 1/3. Notice if the negative was in parentheses and therefore raised to the power of negative 1/4, we would have ended up with the 4th root of negative 81 over here, and we wouldn't have a negative there. So we would basically have 1 over a number that's not a real number, so the answer would again be not a real number. But we didn't have that problem here because the negative was not being raised to the power of negative 1/4. Make sure that you understand this before we proceed. Okay, next we want to look at some conversions from this form, which is exponential, to this form, which is the radical form. So this is the exponential form and this is the radical form of the same basic expression. And we're going to go ahead and use this version of the radical expression where the m is on the outside. So notice that here in the first example, the 17 is not being raised to the power of 4/5, only the m is. So that's a common error where students put the entire 17m under the radical, but here 17 is simply a factor and it's going to carry. So the only power here is m to the 4/5. So we go ahead and carry the 17, and then we multiply it by the 5th root of m, and then raise that to the power of 4. Of course, we could have also written it as 17 times the 5th root of m to the 4. That's perfectly correct as well. Usually they'll specify which of those two forms they want. For example, they'll say write it in the form where you take the root first and then raise to the power. For this next one, we're going to go ahead and realize once again the 2 is not being raised to the power of 1/2. So again, the 2 is just going to carry. So we get 2 times the square root of u. We can write a 2 here in this position, or we normally just leave it out. Definitely, if you're using software like My Math Lab, for instance, don't put the 2 in as part of your answer. So, because that won't be the simplest version of square root of u. What you see is the simplest version of square root of u. For the next one, the 3 is being raised to the power of 1/3. So it's going to go alongside with the v under the radical. So we're going to have the cube root of 3v, like that, for our final answer. All right, number C on the right, we do not consider an expression simplified as long as it has a negative exponent in it. So we're going to go ahead and first take care of that by bringing it downstairs and making it x to the 5/6. And now we go ahead and write the denominator as the 6th root of x, and then raise that to the power of 5. And I'm going to write equals, and you should pause the video and write the other form. That's also correct. And assuming you did that, you got this, correct? And that basically is how you handle those conversions. Make sure you fully understand these before you continue while I clear the board. Okay, so next let's take a look at a few conversions to the other form. We're going to go from radical form this time to exponential form. So again, we will write our main rule down, which is the nth root of x to the m equals x to the m over n. And of course, that's also equal taking the nth root of x first and then raising it to the power of m. So that all three of those expressions are equal. So for the first one, that's a simple matter of realizing that if nothing is written there, we always know there's a 2, which is normally not shown. So, and here inside the exponent is just 1, so we just get 35 to the power of 1 over 2. Remember, in mathematics, whenever you learn an equation such as this or an identity, you need to learn it both from left to right and be able to also apply it from right to left. This bidirectional understanding is always key to success in mathematics, because whenever we teach you how to go from one direction to the other in mathematics, you can be sure we're going to want to learn how to undo that. Therefore, we're always going to require you to go in the other direction as well. So you might as well just make sure you comfortably understand each identity you study or you learn in both directions. So in the next one, we're going to get basically 2 to the power of 6 over 5, and that's pretty much all we can do there. For this next one, we're going to get, well, we can actually look at it and answer it, or we can apply the rule and answer it. Just looking at it, when you look at the 7th root of some number, what does that mean? That means what number do you have to raise to the power of 7 to get this expression? And of course, I think you know what the answer to that is, right? What number do you raise to the power of 7 to get x to the 7? Obviously, x. So you can handle it that way, or you can just, let's see, these whiteboards are a lot touchier than the ones we have in the classroom, aren't they? Okay, so we go ahead and write x to the power of 7 over 7, just so that you realize we can use the rule as well. So that's going to be x to the power of 1, which is of course x. And here we're assuming all the variables are non-negative anyway, so we don't need to worry about absolute values or getting a negative under the radical or anything like that. And as it turns out, in most applications, the radicands are non-negative anyway. So make sure you understand these before we proceed. Okay, so here we have a few new problems. And here's one example where you are actually better off not taking this and turning it into that form first. We're just going to go directly from this form to this form. And we realize that we get 3 to the power of 8 over 4. And that, of course, is just 3 to the power of 2, which gives us a nice 9. Notice if you were to actually take that and turn it into the 4th root of 3 and then raise to the power of 8, that would not have done us a lot of good, because the 4th root of 3 is not a very nice number, or not a very simple number. In fact, it's irrational. So this was actually the better way to fly as far as this problem was concerned. All right, for this next one, it's a very similar problem, just has a variable in it. And again, for all these problems in this section, we're going to assume that the variables are all non-negative. So we're going to get 24 over 6. And of course, that simplifies down to x to the 4. In this next one, you may look at it and say, that's pretty simple, isn't it? There's not a whole lot that can be done, if maybe perhaps putting it into radical form. But notice that there's a negative exponent. An expression is not considered simplified as long as there's a negative power in it. So we're going to go ahead and keep the x to the 1/2 on top, and go ahead and bring down the y to the 1/2, negative 1/2, and down here it becomes y to the 1/2. So then we realize that we can write that as the square root of x over the square root of y. Now later on we're going to realize in the future sections that this will not be considered to be a simplified answer. We can leave it like that for now because we haven't really discussed that, what's called rationalizing the denominator, but we can also write it like this too, just so you get a little feel for how we manipulate some of these expressions. So take a look at all this, make sure you're comfortable with it while I get the board ready for our next set. Okay, next we want to do a quick review of the laws of exponents, because even though we're dealing with fractional exponents now, all the laws of exponents that we had in the past are still applicable. So just to remember, if you recall, the three fundamental properties of or rules of exponents were, we started with the product rule, which was x to the m times x to the n. In other words, you're multiplying two powers that have the same base. When you look at these expressions, remember each of them is called a power. This is called the mth power of x. This is called the nth power of x. The exponent is actually not called the power, it's called the exponent, as we just said, obviously. The number down here is called the base. It's the entire expression which gets known as the power. And so the question is, what happens when you multiply two powers which happen to have the same base? And as you know, we keep the base and we add the exponents. And then the second fundamental property was the power rule, which was, what do you get when you look at a power of a power? And in this case, as you know, the base is kept and we multiply the exponents there. And as you remember, in these rules, the base never changes, with one exception where it completely disappears, and that's for x to the power of 0, which gives us 1. In all the other rules, other than this one, the base always stays. So here, the next rule that was fundamental was the quotient rule, and that one was like this. What happens when you divide two powers with the same base? And as you know, you keep the base, and this time you subtract the exponents. Then we looked at some negative exponent rules, but before we go there, remember the power rule had some relatives. One was, what happens if you take a power of a product? And the answer is simple, just raise each of the bases inside that product to the same power. So you get x to the n, y to the n. And what do you do if it's a quotient? Well, you just do a similar thing. You raise each base to that outer power. And there's also the more general case. What if you have a power inside, like x to the a, y to the b to the power of n? Well, you apply the power rule twice. So you're going to get x to the a n, y to the b n, and the same thing here. If you have x to the a over y to the b, the whole thing raised to the power of n, you're going to get x to the a n over y to the b n. Okay, and then we looked at some negative exponent rules. So we had x to the negative n equals 1 over x to the n. And then we had 1 over x to the negative n equals x to the n. And finally, we had 1 for quotients raised to a negative exponent, like x over y to the negative n to a negative exponent. Remember, we just looked at that a little bit ago. You flip the fraction and then you raise it to the power of n. So make sure that you recall all these. These are really rules that you should have in your toolbox. These are not rules you're going to want to run to a notebook or a textbook for. You want to have these fully memorized, so that to the point where they're so automatic you don't hardly have to think about them. Okay, make sure you have that before we proceed to the next screen. Okay, next we want to look at these next few problems I've written down for you. Notice in the first problem we are multiplying two powers that happen to have the same base. So of course we can use the product rule, which I'll remind you down here. X to the m times x to the n equals x to the m plus n. So here what plays the role of the base x is going to be 3. So we're going to get 3 to the power of 1/2. We add the exponents, correct, plus 1/3. So now we just need to take care of that addition, and of course we need a common denominator of 6. So this denominator is going to require a factor of 3, so we don't forget the numerator. This one is going to require a factor of 2, and we also have to do the same on the top. Whenever we multiply a denominator by a number, we have to multiply the corresponding numerator by the same number. So we end up now with both denominators being 6, so they're now like fractions. We can combine the new numerators, which are 3 and 2. So we get 3 plus 2. I'll go back to black. So we get 3 to the power of 5/6. That's how we handle those. Okay? And if they wanted you to give the answer as a radical, for example, you could do that too. You just get the 6th root of 3 to the 5. And a lot of times when you get something like that, you're going to want to go ahead and work that out to get the 6th root of 243. But usually they just want you to leave the answer in exponential form. So, but if you had to, you can do that too. That's not a big deal. So part B, we realize this time we have a quotient of two powers with the same base. So this time we'll go ahead and apply the quotient rule, which I'll remind you down here. X to the m over x to the n equals x to the m minus n. So we're going to get 5 to the power of 2/3 minus -4/3. And we end up with 5 to the power of 2/3. The two negatives will give us a positive, so plus 4/3. Notice that's going to become 5 to the power of, those are like fractions, we can just combine the numerators. So 6/3. Now of course that's 5 squared, also known as 25. So sometimes things simplify quite nicely. All right, this next problem you got to be careful, because you obviously can't use the product rule here because these are powers but they don't have the same base. However, I do notice that the exponents are the same, so maybe there's something I can do still. And I realize that I have this rule, which I have x times y to the n equals x to the n y to the n. So I'm going to be using this rule going in this direction, right? So right to left. So that means I can write this as 2 times 3 to the 1/2 and I realize that's 6 to the 1/2, and if I wanted to, I can also write it as the square root of 6. All right, so let all this absorb for a few minutes before you continue while I prepare the board for our next set of problems. Okay, so for this next problem, we're gonna realize that this is basically of that general power rule form which we had, which was x to the a, y to the b to the power of, say, n equals x to the a n, y to the b n. So we're basically going to distribute that exponent into both of those powers. So we're going to end up with x to the -1/2 times -2, y to the power of 2/3 times -2. So of course, as you know, -1/2 times -2, that's just going to be +1. So we could write x to the 1, but as we know, that's just x. So here we get y to the power of, and then we can think of this as 2/1, so you just multiply across, you get -4/3. Now, you don't want to stop here, because remember, we don't consider these expressions simplified as long as there's a negative exponents. So we're going to go ahead and bring that y to the -4/3 downstairs and make it y to the 4/3, and then we can stop. Alright, so you should definitely try this next one now that you kind of know how to approach these on your own before you come back to continue the video. Alright, so welcome back. Alright, here we're going to go ahead and apply this outer power first on the top. So we get u to the 3 times 1/2. As you know, that's just 3/2. V to the 3 times -1/2. And as you know, that's -3/2. Now, in the denominator, we have an expression uv, which is being raised to the power of -1/6. So using a similar rule to this, we're going to go ahead and apply the power to each of these factors. So we're going to get u to the -1/6, v to the -1/6, and of course now we can go ahead and apply the quotient rule to the u terms, factors, I should say. And because if there were a plus or a minus here and these actually became terms, we wouldn't be able to do this. But because we only have factors, we can go ahead and do that and apply the quotient rule twice, one for u's, the powers of u, and once for powers of b. So we get u, okay, this unruly board again, let's see, here we go. So we get u to the power of 3/2. It's a good thing the whiteboards at school don't do this, because they're kind of large. That would be problematic. Let's see. Now be very careful here. It's u to the whatever the exponent on the top is minus whatever the exponent on the denominator power is. So it's going to be u minus -1/6. And then v, in a similar manner, is going to be to the power of -3/2 minus, again, -1/6. And of course, one of the common mistakes here is that students just write 3/2 minus 1/6, and they don't write the other negative, which is going to cause problems. So now continuing, we get u to the 3/2 plus 1/6, v to the power of -3/2 plus 1/6. So now we're going to go ahead and find the common denominator of 6 there, and it'll be the same for the v power. Okay, so here we realize that we're going to need to multiply this 2 by a 3 to make it 6, and we have to do the same on the top. This next denominator is already 6, so we don't need to do anything there. So we get 9 So we get 9 plus 1. And here we get, don't forget the negative, we get negative 3 times 2, don't forget, and actually times 3. So let's put this plus back because we have a common denominator, so we have to go times 3 times 3. So actually let's go ahead and write the product. So negative 9 plus, again, we didn't have to do anything to the other fraction, so plus 1, right? So we end up with u to the 10�6th v to the negative 8/6, which is, we can simplify those and reduce, so we get u to the 5/3 v to the negative 4/3. And the last thing we need to do is we need to go ahead and bring the negative exponent downstairs to make it positive. And then we can consider the problem done. Again, if they want you to write it in radical form, just go ahead and convert those to radical forms. So make sure that you practice these. Again, one of the best things you can do in problems like this is pause the video, write the problems down, these two problems, shut down your computer, or just put it in standby, don't look at it anymore, and see if you can carry it out completely on your own. And of course, we have many more problems in your textbooks, in my math lab, etc., that you can practice. But that's how these things get absorbed. You have to practice. That's why homework is so crucial when you go to either high school or college or at any level. Even if you're at the PhD level, you still need to practice this so that you can make it your own. It's the art of the teacher to make things that are complex look simple, and you can only claim they're simple when you have made it your own through your own practice. So make sure that you do that before you continue the video. Okay, next we're going to look at a couple of types of problems which you will encounter in a class like calculus if you decide to take the STEM route. So it'll be good for us to know how to handle these. And of course, here we're just going to apply the distributive property and multiply that x to the 1/2 into this sum, and we're going to do the same thing here into this difference. So starting with the left one, we get x to the 1/2 times x to the 1/2 plus x to the 1/2 times x to the 3/2. And now we're going to apply the product rule, which is, if you recall, x to the m times x to the n equals x to the m plus n. So we get x to the 1/2 plus 1/2 plus x to the 1/2 plus 3/2. And we end up with x to the 1 plus x to the 4/2, which is 2. And of course, when we type in our final answer, we never want to leave it as x to the 1. We always want to write it in simplest form, which is just x. So we write it as x plus x squared. And that's all we have to do there. Alright, so definitely pause the video, see if you can do the next one on your own now before you come back. Welcome back. So I'm hoping you distributed the y to the 2/3. So we get times y to the negative 1/2 minus y to the 2/3 times y to the negative 3/2. And now we're going to apply the product rule again. So we're going to get y to the 2/3 plus -1/2, which just becomes -1/2, minus y to the 2/3 minus 3/2, which plus -3/2, which becomes just minus 3/2. And again, we're going to need a common denominator of 6 here. And that's going to require us to multiply both the numerator and denominator of the first fraction by 2 and the second fraction by 3. And we're going to end up with y to the 4 minus 3/6 minus y to the, we need a common denominator of 6 as well. So we're going to require a factor of 2 on the top and bottom of the first fraction, and again 3 on the second fraction. So we end up with 4 minus 9/6 this time. So basically we end up with y to the 1/6 minus y to the -5/6. And of course, we don't want to leave it like that because we have a negative exponent which needs to be turned into a positive one before we stop. So we're going to go ahead and write that as 1 over y to the 5/6. Of course, there are more things that can be done, but for the purposes of this section, that will be good enough as an answer. Okay, so again, make sure you can do this on your own without looking before you proceed. If you try it once and you don't get it, go find out what happened. What did you miss? Why is it that you didn't get it? This is how you make progress in mathematics. It's the only way you can make real progress in mathematics. Okay, in these next two problems, the power of conversion from radical form to exponential form shines through because, as you know, we have lots of laws with exponents that help us simplify expressions like this. But for example, in the next section, we'll find out that if both of these indices were 3, the situation would be much simpler because then we would be able to multiply under the radical. But because they're different, we won't be able to do that. So the only option we have here is to go ahead and go to exponential form. So this becomes x to the 3/2, as you know by now. And the next one, remember, becomes x to the 2/3. Again, we're using our basic rule, which is b to the m over n equals the nth root of b to the m, right? So here we can now go ahead and apply the product rule. So we get x to the 3/2 plus 2/3. We're just using the product rule. X to the m times x to the n equals x to the m plus n. And here we know that we have to combine those two fractions. So we're going to multiply by 3 here and by 2 here. So we end up with 9 plus 4, or the final answer, x to the 13/6. If they want it in radical form, you go ahead and write it as the 6th root of x to the 13. In the next section, we'll find out that whenever this number is higher than that number, you're going to be able to reduce that. But for this section, we can stop here. So in the next problem, again, if both of these indices were 3, we would be able just to simplify. Well, of course, it would just be the cube root of 1, which is 1, but they're not. Remember, this is the cube root and this is the square root. So again, we're going to have to go to exponential form to get some help. So we get x to the 1/3 over x to the 1/2, and we're gonna end up with using the quotient rule. If you recall, x to the m over x to the n equals x to the m minus n. So we get x to the 1/3 minus 1/2. It looks like we've had a lot of this kind of fraction with 2's and 3's, and that's common actually. So x to the, we need a 6, so once again times 2 times 2 times 3 times 3, so we get x to the 2 minus 3 over 6, which is x to the negative 1/6, which of course we will not leave like that because of the negative exponent. We'll go ahead and leave the final answer as 1 over x to the 1/6. Okay, we're almost done, I promise. So we're going to do just one more example and call it the day. Alright, so there's a problem we want to look at. And you may wonder, why would we want to do this? Well, we're mathematicians, right? We don't have anything better to do. So anyway, basically this is all just for practice. And always remember, if you're going to become a scientist, you'll use some of these, or a mathematician, you'll use some of these in your actual practice. But if nothing else, just remember, think of it as a gymnasium for your mind. Okay, you're just strengthening your logical capabilities, and that's the best way to motivate yourself, because for one thing, perhaps this will motivate you, some research has shown that the more math you take, the more money you make, unless of course you decide to become a mathematics professor. Okay, so here we're going to go ahead and realize that we can go ahead and turn these into fractional powers working from our way from the inside out. So I'm going to leave the most outer power in first, and the second one, I'm going to write the innermost one as x to the 1/2. And of course, I now realize that I can do the same trick again in this inside part. And I know that the cube root of an expression means the expression to the power of 1/3. So that's going to be x to the 1/2 to the 1/3 on the inside. And we still have a 4th root. Finally, we realize that the 4th root of an expression means remember, keep it simple. Just think of all this as just one number, like n, right? So what does the 4th root of n? Well, that means n to the 1/4. So just, it's going to become all of that to the power of 1/4, right? So we end up with x to the, now remember, we can apply the power rule twice, and that means we're just going to end up multiplying all those exponents. So 1/2 times 1/3 times 1/4. So we get x to the 1 over 2 times 3 is 6 times 4 is 24. Or even prettier, we can write it as the 24th root of x. Which brings us to a really nice thing. We can really generalize this and realize that anytime we have, say, the nth root of the mth root of x, we can always do this. We can say that's going to be x to the 1 over m to the 1 over n, which is x to the 1 over mn, which is the nth root of x. So for instance, just as a numerical example, what if we have the cube root of the square root of, say, 64? So we realize, even though nothing is written here, there's a 2 there. So we know that this means we can multiply the 3 and the 2 and just get the 6th root of 64. And if you remember, 64, if you break it down, gives you 2, 32, 2, 16, 2, 8, 2, 4, 2, 2, 2, 1. So 64 is 2 to the 6, right? So we end up with 2. What number do you raise to the power of 6 to get 64? 2. And that's how you do it. All right, so I know that that was a rather long lesson, but there's not much that can be done about it because we had to really cover all this for you to be able to do your work. So that's it. Make sure you practice plentifully and be safe till I see you next time.